dissected the baby. Snap their eyes out, you know. Fun things.
Only good rat is dead rat.
I agree.
Something with snakes. Only good snakes.
I see really
Okay.
What's this one?
Yeah.
Oh, okay.
That's the.
So you're all only here because there were 2 exams in biology today. Right?
And the botany exam.
I love this
I thought we were
topic.
doing our test back.
It's my last class. Cool.
There's a botany exam this morning.
I just am a good student, so.
If I only had
Here I
A&P
am.
exam, I would not be here. I will be very.
I'm proctoring 10 exams today, but it's not my exams. Are you going to never give me exams?
I'm here because I enjoy learning organic chemistry.
Shut up,
A
Dan.
lifelong learner.
I literally, like, could have guessed you were the only one to
So they're here.
but they're not here.
See what's wrong?
They're
probably
here, but
studying
are
for
they
the
here?
AP test.
Shane! Look who came to class. Wow, Shane, I have a
Shane
spot
too.
right
I
here.
knew Shane would be here.
So what was wrong with the last thing that I wrote on the board? I said everything that I wrote on the board was factually correct.
Was
Every
it-
step in the mechanism is correct. Every arrow starts at the right position and goes to the right position. Every atom was supposed to have 4 bonds, had 4 bonds. Every atom was supposed to have less than 4 bonds, had less than 4 bonds. All there, it's all correct. Why is it wrong?
Does that have to do with the bromine? And
No.
Does that have to do with the 3rd step?
Because your product is useless.
No,
It's
that is
impossible
very
to make.
useful because you just built in a leaving group. I built a leaving group into my carbonyl, and now I can make new, bigger and twisted carbonyls.
Is it because it was on the alpha?
No.
Is it because.
I said there was nothing factually wrong with the mechanism. There was something philosophically wrong.
Ethics.
It.
That's always the answer to bio.
Surface area.
What was it about those alpha hydrogens that we were monopolizing on?
They're acidic.
They're acidic. And what were the conditions of my reaction?
You need.
We put in acid.
You need acid
Okay,
water.
so if I was trying to explore the acidic nature of something, would I really put it in acid? No. What do acids react with?
These.
So why did you put your stupid reaction in acid?
Because he told us to.
I know. and nobody's thought to say, stop! You're mixing acids together. That makes no sense. If you do the reaction in acid, one of the alpha hydrogens gets replaced by a halogen. However, if we do the reaction in base, then all of the alpha hydrogens get replaced. And that is called perhalogenation. What's the product of the top reaction?
Just one bromine
Where does it go?
on the alpha position.
About this one.
Could you do? Well, there's the answer of 2 bromines on one alpha position, but could one bromine go on both alpha positions?
Is there a reason why not?
What?
Is there a reason why not?
I don't know. That's why I'm asking.
No.
Okay.
No, there is not a reason why not.
I'm confused. It's not the same thing.
I haven't written where the bromine is yet. Where does the bromine go?
On the alpha position.
From the same place.
And the carbon attached to the oxygen.
Alpha to that carbon.
On the other side. This one.
Oh wait, they're both acidic. Wait, what?
Okay, let's ask this a different way. What's the name of this product?
2-bromo cyclo or hexacyclo hexon. Hexanone.
Okay. What's the name of the product below it?
2-bromo cyclo hexanone.
No. Because that would be the same as the one above it. And that's not what happens. We haven't filled in where the bromines go.
So there's options?
Are these under different conditions?
Oh wait, does it go into a does it break the ring?
No.
Oh.
They're both
They go to the alpha.
on the same carbon.
This does it once.
Did you need it
And
with
this does it.
They're
Well, I
both-
haven't written the product down yet because you haven't told me what it is. Don't tell me that they're the same.
So
I'm
Two-
waiting for you to tell me.
you have a
Dibromo.
bromine on either side.
Okay. Who thinks that's the product? At least you're going out on a limb. That's a rational answer. No, it's wrong. Why is it wrong?
They're on the same carbon? They add to
or
the same
one of
carbon?
the
What's the name of my product?
Dibromo cyclohexanone.
oh, or 2-2-2-2 tetrabromo.
It's not 2222.
2, 4.
No, it's 2266.
Oh,
There are 2 hydrogens here. They all go. All available hydrogens.
is this supposed to be basic?
I was so confused.
See, we're not dumb.
We're just confused.
Rewind the tape. Rewind the tape. Okay, my bad. base, you get perhalogenation. That means everything that's available, alpha positions, get brominated. I didn't realize I've written the same thing down. It is a Friday. So this gets to be 2266 tetra.
Could you explain the alpha thing briefly?
Mm-hmm. Alpha notation does this. Instead of just numbering everything, what we do is we find the area of interest in our molecule. That's the functional group. Functional groups used to go, I don't know if anybody still uses this word. Moiety. I'm just throwing it out there just in case you see it somewhere. That's the functional group. That's the thing that if you look at this molecule, that's where your attention should go to. This is the place that should be doing the reaction. But there are times when reaction happens somewhere else in the molecule and not at the functional group. And when that's the case, we need to start counting. And we count positions away from the functional group. And we call them alpha, beta, gamma, delta, epsilon, blah, 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 lambda, iota. Did anybody learn Greek between Wednesday and today?
No.
And it is possible that in a molecule, there can be a left and a right. So this is also an alpha. Now, if these two alphas are different from one another, and for some reason that's important, we can call one of them alpha prime. It's not going to be an issue for us. Okay? So alpha and beta are the ones that get used the most. It just tells you how far away from the interesting thing you are.
Okay.
And in this reaction, there's my functional group. That alpha hydrogens turn out to be a tiny bit acidic, little tiny bit acidic. And in acid, you can change one of them. But in base, and the tape will prove when I rewind it that I wrote base down. Because I'm going to Photoshop that in.
It's like little square form.
You take them all. Monohalogenation, perhalogenation. Okay. That leads us to a special case. There's a reaction called the Iodoform reaction. And what this is, it is a perhalogenation of a methyl, it has to be a methyl ketone in base, which kind of starts to roll out, not quite out of control, but just progressively get more and more reactive to the point where it becomes an oxidation. So oxidation of a methyl ketone becomes a carboxylic acid. That's not supposed to happen. Aldehydes get oxidized to carboxylic acids, ketones don't. But this one does. Plus something called iodoform. Guess what the iodo means? Yeah. What does the form mean?
Formic acid kind of deal?
Yeah. What does the form in formic acid mean?
Ants. Ants. The number.
Yeah, well, formica is the word for ant, because formic acid is the acid in ant bites. But for us, chemists, form means the same as meth, one carbon. One carbon. Anybody know what that is? Should be trichloromethane. Or is known as chloroform. Guess what that is?
Bromohydride.
That's iodoform. Okay, so we're going to make a carboxylic acid plus this. Chloroform is a colorless liquid. Doesn't smell so great. It's an anesthetic. You can soak a rag with that and then take turns in anesthetizing Axel. It is not a particularly reliable anesthetic. Iodoform, iodine's used in medicine because iodine is antiseptic. If you've ever been into like yesterday, the biology people were dissecting baby rats, and I didn't want to see it. If you've ever been into a operating theater, and they're operating on people, they will take a bucket of iodoform, iodine, and just paint you with it. They'll just paint everything. It stains you orangey, yellow, brown, color, and it's antiseptic.
Iodine tablets. Iodine tablets. For water.
Uh-huh. Does it turn them brown? Does it turn the water brown?
Sort of.
Okay. Because iodine, under some circumstances, will be purple. As a vapor, as a crystal, it's purple, but in solution, it's usually that orangey, browny mud color. And I did a stint at the VA hospital as a management consultant, and so I've seen the inside of many, many, many operating rooms, and they paint those people up. Okay, let's do it. So all I need is methyl ketone. Let's pick one that only has methyls on one side, because that's going to make life for us easier. Here, not only is this a methyl ketone, so it fits my description, it only has alpha hydrogens, the slightly acidic ones, on one side. The good news for us here is that there are no alpha hydrogens on this side. So at some point, hopefully soon, I'll throw up a review for your next test. And sometimes when you're looking at the questions that are being asked on the review, you'll figuratively or literally shake your fist and say, why is he asking me such tough questions? Because the structures for some of the reactions look complicated. And then when you think for a second what the question is asking, you'll go, oh, I know what he's doing. He's stopping me from having a reactive site on this side. He's actually making it easier for me. So sometimes when the reactions look, on first sight, difficult on paper, they're actually making it easier. Okay, that is acetophenone. Nice, liquid ketone. I'm going to start writing all the bonds out again. Because in base, all right, here's where things, we're now going to have to start to use our discretion. In hydroxide, shouldn't hydroxide just do this?
It's a nucleophile.
Yeah, I know, but can you tell the bottle, can we go to the stock room and be the base whisperer and tell, hey, hydroxide, don't be in a base this morning. I want you to be a nucleophile. No, it doesn't know. We've told you that ketones and aldehydes in the presence of hydroxide do nucleophilic what? Addition. There is no leaving group, so there cannot be a substitution. In the presence of base, nucleophile, I should be doing a nucleophilic addition. So I have to tell the base to cut that out. Here's how I do it. If I make the base dilute, then it doesn't act as a nucleophile. How many times did you hear me say it's always easier to be a base than it is to be a nucleophile? Why? Give me several reasons, but start throwing them at me. Why is it easier for that to be a base for this molecule than it is to be a nucleophile?
Hydrogens are more accessible.
Hydrogens are on the outside of the molecule. They will always be on the outside of the molecule because hydrogens in group 1 can only ever make terminal bonds. And until you come to take my inorganic chemistry class, that remains true. It becomes untrue in 3301. But hydrogen is always terminal. It's always on the outside of the molecule. Therefore, the base is concealed. What else?
Carbons are hard to reach.
Okay. And?
Hydrogens are acidic.
I can do that. Or I can do this, or this, or this. There's 3 of them. There's only one of those. The carbon's outnumbered, 3 to 1. So if I make my base dilute, I tell it, just go do the easy thing, and we'll worry about the difficult thing later on. In dilute base, we're going to see basic behavior. To up the concentration of base, you're going to start to see nucleophilic behavior. Keep that base low. Okay, so I'm going to take that hydrogen. Now, we can either do this the correct way, or we can do it the shortcut way.
Correct.
The correct way is to take those electrons, put them in here, and shuffle them up. It's always best if you show your sp2 carbons as sp2 carbons. There is my base. And even though it's dilute, there's going to be a lot of hydroxide floating around, even though it's dilute. I'm not really worried about it. Okay, that's the correct way. Anybody know what this is called? Okay, look. What would this be called? What group is that?
Enol.
That's an enol. If I take the hydrogen away, negative charge on an oxygen. Word in chemistry where there is a negative charge and an oxygen ends in
Oxide.
Ide means negatively charged. Ate means negatively charged and contains oxygen. This is an enolate. Okay, that's the correct way. Let's show you, I'll show you the cheap way. The cheap way works just as well for this reaction. The cheat way is take your hydroxide, just localize it on that carbon. Now the correct way, in the second step, is the bromine. And in the correct way, you reform that carbonyl, you reach out to the bromo that's at the front, and you disconnect the bromo that's at the back. In the cheat way, do this. And they both end up with the same answer. Oh, it's not bromo. It's not a bromine. It's not a bromine. It's not a bromine. I didn't write bromine down. It's not a bromine. It's not a bromine. An iodine. Should be iodine. Fluorine, chlorine, bromine, iodine. Astatine. Should be bromine. Lots of bromine. Iodine. Okay. So whether you do it the cheap way or whether you do it the real way, you end up with the same thing. Okay? I will accept both. The reason that this hydrogen is a little bit acidic in the first place is because you had pulled its electrons away from it by resonance up into that carbonyl. See this hydrogen? That hydrogen is still an alpha hydrogen, but now it's having its electrons pulled up into that oxygen, and iodine's a group 7 element. It's not electronegative like a fluorine, but it's going to be pulling electrons. So this is now more acidic than the first. Alpha hydrogen. So this next step gets faster. The hydroxide grabs hold of this hydrogen. The hydrogen dumps its electrons, makes the enolate. I'm going to write it out the correct long way. If you want to take the shortcut and do it this way, I am totally fine with that. And in fact, as you progress through this reaction, there is actually more of a case of saying that negative charge could be localized on the carbon rather than distributed up into an enolate. Reform the carbonyl, reach out, grab an iodine. Now, the remaining, I've got an iodine that I got some iodides that I just have to account for. And some H2O. That remaining alpha hydrogen right here is not highly acidic, but more acidic. Which means that the next step is even faster. I'm going to write it, pointing downwards a bit so that I can squeeze it onto the board and perhaps still be in the frame of the camera. So here's my hydroxide. Take that one, put it here, open that up to an enolate. Floating around, and then here's another molecule of iodine. That carbonyl reforms, reaches out, grabs this, and I do 3 back-to-back halogenations. So at this point, I have achieved my perhalogenation. Okay? That is the perhalogenation product. All the alpha hydrogens have been removed. Now, this is a special case. If we had done this with fluorines, I make the perfluoroacetophenone at the alpha. If it's a chloro, I make the trichloroacetophenone. If it's a bromo, I make the tribromoacetophenone. But with the iodo, something different happens because bromoform and chloroform are different than iodoform because iodoform is a precipitate. It's a solid, and the other two are liquids. What's going on now there is electron withdrawal this way, and that way, and this way. What do you think it's doing to the strength of that carbon-to-carbon bond right there? Because these electrons are, these groups are all pulling electrons away from it. What's happening to that bond?
It's getting more acidic. Or
It's getting weaker.
dissociating, yeah.
It's getting weaker. And what do weak bonds have a habit of doing? Yeah. And if I break off right next to my leaving group, functional group, that makes me a leaving group. Leaving group. So now I still have hydroxide floating around. That hydroxide's looking for any acid that's in solution, and it can't find any. Perhaps it's time to be a nucleophile. After it's done being an acid, or hunting out acids, it now goes looking for a nucleophile. And this molecule now has a leaving group. I'm going to do a nucleophilic acyl substitution rather than the nucleophilic addition that I would have done in my first step. Hydroxide here gives me an addition. Hydroxide here gives me a substitution. Got a negative charge in my molecule. I'm in base, so there's nothing that I can reach out to that's acidic to grab hold of, because there are no H pluses in this solution, because my solution is in base. So that carbonyl is now going to seek to reform, and it's going to kick off whichever one of these three groups is the weakest base. The hydroxide, the phenylcarbanion, or this thing that's experiencing three equivalents of inductive loss. And kicks that off. That gives me carboxylic acid. So I just oxidized a ketone to a carboxylic acid. That's impossible. That's not supposed to happen. And it can only happen with methyl ketones, and it can only happen under these conditions. Plus CI3. And that is a negative. So it's going to look for the most acidic thing that it can find. It's right there. So you end up with the carboxylate and iodoform. And iodoform is a yellow precipitate. So for many years, this reaction was used as a test, a spot test, like in a test tube, for methyl ketones. I have two ketones. The labels have come off the bottles. I know that one is 2-butanone and the other one, I know that one is 2-pentanone. And the other one is 3-pentanone. But the labels have come off the bottles. I put them both in test tubes. I add some base, and I add some iodine. Whichever one goes yellow is the methyl ketone. This used to be a test for methyl ketones, and is a kind of a rule breaker that we can oxidize that up.
I have a question. For the hydroxide, the last time you used it as a nucleophile.
Yeah.
Could you use like water instead? Because that's there too, right?
Yeah. So why would you?
Well, I thought about when you protonate that water, because there's 3 bonds to that oxygen after you do it as a nucleophile, that breaks off and that hydrogen attaches to the broken off iodoform that's missing a hydrogen.
You're going to have to. There's going to need to be a step 2 because you cannot isolate. Well, that's going to actually be the sodium salt, right? Because you're using sodium hydroxide. So I just made my sodium benzoate. Sodium benzoate is going to be guaranteed to be soluble in water. And this is all in water, dilute. So dilute base right here. So my product is currently floating around in the solution and I cannot get it out. My iodoform is at the bottom of the flask. If I do the acid workup here and pick up that, and I make benzoic acid, and it turns out that benzoic acid is only partly soluble in water. So if I do this and I chill the reaction flask, this will also precipitate. So it has to be followed by this. Technically, your iodoform reaction goes up to this step. But you've got a negative charge here. You're going to need to use the acid workup. So you're saying, well, what if I did the acid workup here, then I could use just water as a nucleophile. Now do it at the end. Okay. That's all I got. I know, I got 5 minutes early for spring break. Don't get sunburned. Don't get arrested. Be careful driving.